Hello, everyone, and welcome to this Lorandom podcast. I'm your host, Peter Baumann, the editor-in-chief at Lorandom. And today we are continuing our Friday podcast episodes as companions to our Monday editorials. And this Monday, we released a very special piece with Ian Goodfellow on the birth of GANs. And today we are releasing the full conversation. So Monday was basically part one. This is now the full conversation with the legendary machine learning and deep learning engineer, Ian Goodfellow, who was also the inventor of GANs. So besides inventing GANs, Ian is just a legend. He has nearly 400,000 citations on Google Scholar. He literally wrote the book called Deep Learning with Yoshua Bengio and Aaron Corville. This is honestly one of the interviews I've been looking forward to the most. Ian's been someone that I've wanted to talk to for years. He's had this singularly outsized impact on image making in the 21st century, and it really hasn't been explored. He doesn't give many interviews. He hasn't spoken extensively in public in years, and he's never given an interview in this much depth about culture and specifically his impact and GAN's impact on culture. So this is an incredibly important story, how GANs were born and their impact, and I can't wait to help tell it. And thank you so much for listening. Let's begin. Yeah, maybe just to start, I know, so it's been about 11 years since the paper. It was the summer of 2014. And there was even this retrospective last year at NeurIPS 2024, where they looked back at the legacy of GANs after 10 years. Yeah, it was interesting because, of course, it focused on the extensive technical legacy and the development of deep learning over the last 11 years, but not that much was made about the kind of cultural impact. Yeah, the cultural impact has been quite large, and I think not quite as explored as maybe the technical side. So yeah, I'm excited to get into some of that today. And one other area that we're kind of beginning from is this idea that multimodal media generation is important even historically and art historically, and in the relationship with art and technology, like even as important as the advent of the digital or the internet. And it has been compared to this new paradigm for media, and even moving forward basically for the next century. GANs played a really significant role in that initiation, or in the development of deep generative models, and especially turning them from something more theoretical to tasks that are actually based on synthesis and generation. So maybe we can start with can you explain briefly what GANs are and what they do? And then we can talk about in a very simple, maybe broad way. And then we can talk about the story of how they were developed.
Yeah, and I think that turn to focusing on synthesis and generation of media is also something really crucial to touch on. And I think some of your questions get at it. And the story there might be more interesting than some of the questions might land on. But yeah, so to start with explaining what GANs are a solution to the generative modeling problem. The generative modeling problem is, broadly speaking, you have a data set containing a lot of examples of something. For GANs, that's usually, we like to use photographs as the example of the something. So maybe you have a lot of photos of faces. Those faces all come from some probability distribution. And we want a learning algorithm to learn the probability distribution of realistic faces and then generate more faces like them. GANs do that by having two different neural networks compete in a game in the formal game theoretic sense. One of those neural networks is a generator network. And you can think of that one as kind of like an artist. And the other network is the discriminator network that you can think of as kind of like an art critic, except it's not really a stylistic art critic, but more just when it looks purely at realism. In the game, the generator produces a photo of a face, and then the art critic looks at either real photos or fake photos coming from the generator. And for each individual photo that the art critic sees, they have to estimate a probability of whether the photo is real or fake. And the generator gets a learning signal based on the probability coming from that art critic. So the generator tries to drive the art critic's probability up toward 1. The art critic tries to drive their probability on fake samples down to 0, and their probability on real samples up toward 1. We can actually analyze this with game theory and show that the Nash equilibrium, so kind of the point at which neither player can improve their strategy, is for the artist to learn to produce perfectly realistic photos of faces, and for the art critic to have to essentially do a coin toss on every photo because all the photos will be perfectly realistic. And back in 2014, that sure seemed theoretical to most people. I think in 2025, we're now seeing that AI fakes can be good enough that it's really, really hard to tell.
Yeah, and maybe I think it's what's so interesting too is that GANs had this rich technical and also cultural impact, but the story of them is also really interesting and also I think unique in that it happened all quite quickly. The idea happened quickly, the paper happened quickly. So I wonder if we can talk about the story of how GANs came to be 11 years ago, and there's kind of a now famous story out there about a night. It was in Montreal, is that right? And I believe even the date, I've got the date, was May 26th, 2014. So again, like not too far from when the paper came out. But yeah, so just beginning with that origin story, it was this grad student sent off in Montreal at a bar. What do you remember from that night still?
Yeah, that date sounds correct to me. It was about 2 weeks before the deadline for NIPS, the conference that's called NeurIPS now. I had not been planning to write a paper for NIPS that year. I was working on writing the deep learning textbook instead. I think one thing that's important to understand is, in terms of the speed that everything happens, everyone involved in this story had been working on neural nets and ideas related to generative modeling for years beforehand. We weren't trying to solve the generative modeling problem per se, but a lot of us had thought that using generative modeling as kind of a practice exercise might help neural nets to solve supervised learning, where you show the neural net a face and you ask it, for example, is this person smiling, frowning, and so on. And by 2014, it had turned out that you could solve the supervised learning problem without having to do a warm-up using generative modeling. But all of us had a lot of practice doing generative modeling for several years beforehand. So we all had kind of ideas floating around in our head that kind of clicked into place on this night. It's not that the ideas came out of nowhere on this particular night. I had not been planning to write a paper. I'd actually been working from my girlfriend's house, writing the textbook. I had handed in my thesis. I was basically done with grad school. And so my lab mates hadn't even really seen me very much for a little while. This party was a going away party, both for me and for my colleague Razvan Pascanu, who was going off to DeepMind. Since it was their first time seeing me in a while, some of my fellow students were asking me for programming advice. These nights at the bar often ended up with, friendly academic debate and sometimes kind of friendly software engineering strategy debate. And in this case, we ended up in a pretty big disagreement about how to solve the problem that they were asking me for help with. So they were saying that they wanted to make a generative model that had essentially a generator that would spit out photos, and then they wanted to check if the average brightness of all the pixels in a batch was correct. And then they wanted to check if the correlation between all the pairs of pixels in the batch was correct. And then they wanted to check if the product of all 3 pixels for all triplets of pixels in the batch was correct. Just checking pairwise correlation won't get you very far in terms of getting a realistic photo, but they thought maybe if we bring in triplets of pixels, we can start to get interesting structure in the image. The problem is there's a whole lot of triplets, right? Like if you have 1,000 pixels, which isn't even very many pixels in an image, you're already talking like a million triplets. They were asking for advice for how can we try to write a program that is able to process so many triplets. I was walking them through the math of, well, here's how many pixels are in your image. You're going to process not just one image, but a batch. Here's how much memory is on the GPU. You're not going to be able to program your way out of this. There's just too many triplets. And so what I told him instead was, how about instead of trying to make a big long list of all the triplet features, what if you have a neural net learn the features that you should look at and have a list of, like 1,000 features that you think describe what you're looking for in the photo. And that was essentially the embedding space of the discriminator network is what I was describing. So have a discriminator network, keep looking at the photos, and the last hidden layer of the discriminator network gives you a set of 1,000 features that you can track. Instead of having, for a good-sized image, it would be like billions or trillions of triplet features. And they were essentially saying, it's hard enough to train one neural network. You can't train a second neural network in the inner loop of training the outer neural net, which is a fair objection. I mean, that's a lot of why GANs are not the state of the art in generative modeling today. This idea worked well enough that it kind of got the ball rolling on image generation, but it did eventually get superseded by ideas that didn't involve this layer of complexity. But at the time, we didn't know of a great alternative yet. I think the context of being at the going away party and having just a little bit to drink, I think a lot of the time having your inhibitions lowered just a little bit is useful for trying out an idea that you wouldn't try if you were, in the lab, analyzing things really coldly. There's a lot of ideas that you might shoot down just a little bit too early. My fellow students really didn't want to try it out. I did want to try it out. And I actually had quite a lot of code lying around from a previous paper that made it pretty easy to glue together. We had a previous paper on just the supervised part where I could take the supervised model and use that as the art critic part, the discriminator. And then I could essentially copy paste that and turn it upside down and make that the generator. And then the only new piece of code I really had to write was a little bit to say, like, flip the learning signal around and follow it backwards. And that becomes the learning signal for the generator. So when people hear that I wrote this really, really fast, it's not that I wrote it from scratch. It's that I had a really good code base already set up with all of the instrumentation and tooling to make it easy to make changes really fast. The other thing that was important was I got incredibly lucky that the first time I ran it, it worked. A lot of the time you code up a new idea and there's lots of different settings you have to set on a neural net. When you update the weights, how big should the update be? How big should each layer of the neural net be? How many layers should there be? Just dozens of things like this. And a lot of the time you have to launch a job at a computer cluster and search through dozens of different combinations of settings before you get anything reasonable. I was really lucky that just taking the best settings from supervised learning from an earlier paper and just copy pasting everything, even though I was taking it and flipping it upside down for the generator, just worked on the first try. The first thing that I trained was taking little images of handwritten digits from a data set called MNIST that's really overused in machine learning research, but it's also very fast to train on. And the very first time that I trained on it, it worked. And for anybody that was used to the previous generation of deep learning generative models, Boltzmann machines, just the ease with which that happened made it really obvious that this was something different. That with Boltzmann machines, you spend quite a lot of time struggling to get them to produce recognizable MNIST digits, and this just went ahead and spat out MNIST digits in like 2 minutes. And from that, I was excited and went ahead and emailed the lab more or less right away.
Were those initial MNIST digits, which were, I guess, the very first GAN images, were they the ones that you used in the paper, or are they just like, are they lying around somewhere? Or what do you have them?
I don't know whether they're the ones I used in the paper. I could try to figure that out by diffing them. I do have them. They're just in my Gmail outbox. I could forward them to you.
Yeah, sure. That would be really interesting to see.
Yeah.
Those are, yeah, because I guess if those were the GANs you created the very first night, I mean, obviously those would be the first
Yeah.
ones. Oh, even though, of course, they would look very similar to the ones in the paper if they're not.
Well, but it's a grid of random digits. So
Oh, okay.
if it's a different set of digits, it probably, one of them would start with like 759 and another one would start with 304. So
Right.
it should be easy to tell if it's a different grid.
Yeah.
I can check and I can send you the original ones.
Yeah, sure. That would be amazing. So part of the lore of that story and that night is also that I think you stayed up all night to do that. So you got home from the bar, and then what time would that have been?
Oh,
Maybe.
no, not all night. My girlfriend she hadn't come to the going away party. I think she had work the next day, and I was only writing the deep learning book, so setting my own hours. So I was awake after my girlfriend had gone to sleep, but I only stayed up like an hour after coming home because it was very fast to get it working. Later, I did end up pulling an all-nighter while writing the NeurIPS paper. And there, the funny story is, my girlfriend was talking about like, are you working too hard? Like, is this good work-life balance? Not saying I shouldn't, just like checking in and evaluating, like, are we making good choices here? And I was saying, like, yeah, it's definitely worth it to pull an all-nighter for this. This is going to be bigger than max out. And now everybody that hears that story is like, what's max out? Yeah. And and so max out was a paper I wrote that was the most cited paper of ICML 2013, which we had thought was a huge deal up until GANs, and then clearly GANs were the much bigger deal. Yeah, but the all-nighter was, like a week and a half later, closer to the deadline to submit to NIPS.
Right, because I think, like you said, it was about 2 weeks or 12 days from the NIPS deadline, and so the very first night I got the MNIST samples. I think the next day I sent them to the lab. I hadn't been going to the lab in person. I went into the lab and kind of said, like, I had been telling everybody I've had it in my thesis. I'm not doing research anymore. I'm writing a deep learning book, but I've got this idea. Who wants to write a NIPS paper with me? And a bunch of people in the lab were like, you have my sword, you have my bow. And then we all worked really hard for 2 weeks and shipped the paper. In that 2 weeks that you worked together, were you going in person and meeting every day, or was it mostly a collaborative effort? Or
once I realized I was writing a paper, I was back to going into the lab. I was back in grad student mode, and the paper was really very collaborative. I guess during that Test of Time Award talk in 2024 last year, I was I was too sick to go and do the talk, but my co-author David Ward Farley did the talk. We really emphasized that it takes a village to do this kind of thing, and so first all of the co-authors each made important contributions, but beyond that, the lab itself was the kind of environment that it took to be able to do this. People like Frederic Bastien, who was a lab employee, developed and maintained tools like Theano, the software library that we used for all of our research. He actually had been working on a feature for Theano that we realized we needed to be able to finish the paper, and he rushed and finished it in time for us to be able to write the paper. So this is like a massive collaborative effort involving, people on the paper, people not on the paper who are credited on the Theano publications rather than on the GAN publication, that kind of thing.
So from what I understand is that basically after that paper came out, this kicked off an intense competition to get this going at higher scales and different and higher resolutions. So like, how quickly after you presented it did you get the sense that this would be something that the community was interested in? I mean, well, I guess you knew it before you even presented it, but was it right away that you presented it? That was there noticeable interest?
There was noticeable interest, but it wasn't the kind of intensity that came later. It wasn't also, I guess a lot of things in machine learning get out of date really fast, right? Like a lot of the time, things are more like the example of max out that I gave, where it's the most cited paper of ICML 2013. You see a lot of people use it in their papers the next year, and then people move on to something like ResNets pretty soon. So there's like a pretty short lifespan of something being state of the art. What was a bit more surprising about GANs is that they stayed really popular for like at least 5 years. And even now they haven't totally died. Like there's still adversarial training as a component of a lot of image generation systems. So the longevity was more surprising than the popularity, if that makes sense. Like a lot of things become popular briefly and then get replaced. So pretty early on I could tell, like, yeah, this will definitely be like the flavor of the year. I didn't realize that it would last longer than that. I think the first point where I realized that it had pretty big traction was LapGAN, which actually was like a bit slow. That was when there was really high quality, high investment work following up on it. So LapGAN was, LAP stands for Laplacian pyramid, where they kind of scale up the image to several different resolutions. And that actually took about a year after the first GAN paper.
That was Sumit, right? And Facebook?
Yeah, he's the second author. The first author is Emily Denton.
Yeah, it's interesting that it maybe took a few months, but I know like by that winter of 2015, like Dr. Fei-Fei Li had a course at Stanford where GANs were at least mentioned, and I think that helped get some attention to them. And then, yeah, Sumit and Facebook and Emily Denton worked on them. And then by early 2015, and then I guess kind of unbeknownst to people at the time, but Alec Radford was also working at them at Indico in early 2015. And
yeah.
so, yeah, it definitely kicked off a lot of different channels of interest right away. And
yeah, so DCGAN was, that became public like November 2015. And that was
over a year later.
That was kind of like the corner of the hockey stick, where that was when it did really take off. I think LapGAN was when I was like, yeah, this is definitely going to go somewhere. And then DCGAN was like, okay, this is when it actually is going somewhere.
Yeah, it was remarkable that right after Alec posted the DCGAN paper, like how much different artists started picking up on it and how much attention it got. And yeah, you really could see even from looking back that it sparked a lot at the time, on social media as those things were coming. So you mentioned you're working on your book a few times, and yeah, I think it's an interesting way to frame deep generative models in general, because there's a diagram in your book that it basically, the way that the diagram presents deep generative modeling is as this culmination of deep learning. And it seems to be presented that way in the book. And yeah, just to kind of frame the impact of GANs and deep generative modeling. Yeah, do you see deep generative modeling as this kind of culmination of deep learning?
I mean, that's kind of the way the industry has gone, but that's not what we intended with the book. If you read the intro to the book, we actually say there are important topics that we aren't covering, like reinforcement learning. I think at the time that the book came out, like 2016, a lot of people viewed deep reinforcement learning as the culmination, and the fact that we weren't covering how AlphaGo worked in detail. I think a lot of people viewed AlphaGo as the culmination of AI at the time. None of the three authors of the book had enough RL expertise to write a good chapter on RL, and so that was actually viewed as kind of a defect of the book. The order of the book is more based on kind of two principles. One is, if people start reading front to back, we want them to go in sort of the order of prereqs. So we start with like all the math fundamentals that they need to be able to understand the math later on. And so partly generative models are at the end because they have the most prereqs. And then the other thing is we try to order it in terms of least likely to get outdated to most likely to get outdated. So like at the start of the book, there's like linear algebra is not going anywhere. And then at the end of the book, we're like, here's Pixel CNN, probably going to be out of date by the time we print it. And so we're moving sort of from general to specific. And by the time you're talking about deep generative models, you have to be pretty specific. No, I don't think generative models are necessarily the culmination of deep learning. There's a lot of other interesting things you can build on top of deep learning. The way the industry has gone, it's been a little bit surprising that almost everything powerful we have built has had a generative model in it for several years. But when we wrote the book, it felt more like we're all generative model experts and we're sort of biasing it toward what we know. Turned out we knew something pretty powerful. But we actually felt sort of like, oh, if we knew RL, we'd put an RL chapter in there too. And it would have been sort of arbitrary which one came first and which one came second.
Yeah, and it's also interesting at that time. So there were these sort of two early deep generative models. There was GANs and VAEs, right? I guess that could also be considered a deep generative model. But before that, for years and decades, they had been theoretical and they couldn't generate anything. Like we said at the beginning, they were used for things like feature extraction and feature learning. Yeah, it was really VAEs and GANs that started changing that. I'm interested also in just what you think GANs can and can't do on a kind of more theoretical level. So one way that I know from the art world that GANs have been criticized, I know back in 2020, Mario Carpo wrote something for Artforum, but this criticism has been around. Many people have said it. I think maybe his is just one of the more well-known ones, but they're usually reduced or flattened to something just like mimic machines or style transfer, and usually said in a derisive way, especially when talking about art where those are kind of pre-modern notions. And I just wonder, do you think that that's an accurate representation and understanding of what the technologies can do?
Yeah, and I did a talk at a machine learning and art workshop where that was essentially my thesis. I try to be a little bit humble and stay in my lane. I don't have any art credentials or any philosophy credentials, but if I look at the dictionary definitions of words like creativity and imagination, those words are subtly different. Where I would say imagination just means being able to kind of conjure up a sensory experience in your mind that isn't driven by your senses. Like, can GANs create an image that isn't actually there, being driven by, like camera sensors? Well, yeah, certainly that's what they're designed to do. Creativity seems to require more novelty than is what is there in GANs. Like GANs are by design meant to go for a very specific kind of novelty where they're told, we want you to draw a new sample from the same distribution, but we very intentionally don't want you to try to invent things that wouldn't be in that distribution. So you explicitly don't want it to be Picasso. Like Picasso is out of distribution. That's more creative than the specification for GANs. So I'd say that they have imagination but not creativity. Then there's a lot of interesting stuff about, like, do you have to use GANs in the way that they're described in the training process, where like all you do is you train them and then you draw samples from the distribution from them. And we've seen people like take their decoder and use them to make paintbrushes and things like that. And then they can become really interesting tools for creativity, where the human is the creative one and the GAN is providing a function that's really different than just drawing samples from the distribution. But it's still not the GAN that's really being creative. Yeah, the part that's philosophically different is like, when you mess around with materials and the materials give you an interesting effect, are you calling the materials creative? Like the process has given you an interesting effect there. And I'd say kind of the same thing is happening with GANs. Like when you get an interesting paintbrush out of a GAN, I don't feel like the algorithm had intentionality there. It's more like you trained this thing and it turns out that like if you crack its brain open, you found an interesting paintbrush in there. But the learning algorithm wasn't trying to make an interesting paintbrush.
So when you've said that they can do more than mimic, what you mean is when humans intervene with them, humans can mold them to do something more than mimicry, but on their own, what they fundamentally do is mimicry. Is that what you're saying?
Yeah. Like when you start poking around inside and say like, oh, I found this really cool brush. That's the human being creative.
Yeah, so that's also really interesting, and that's also something that Mario Carpo, a couple of years later, returned to when he returned to a criticism of GANs, and I don't mean criticism really in a negative way, or just of AI art, which is almost nearly synonymous with GANs for quite many years. And yeah, what he then was talking about is that the machines can do interesting things, or the technologies can do interesting things, but they need that human creativity. So you would agree that they can be separated, or
I think what gets more interesting is when you get to the era of like text prompt driven conditional models. So which GANs didn't really participate in that much. There is, for example, GigaGAN, which is one of these large GANs that have been trained to go from text to images. In the generative model framing, those are still basically just trained output an image from the probability distribution of images conditioned on that text. But we're also seeing that those models do get trained with reinforcement learning and human feedback. So companies like Midjourney asks users to rate images. Like you can actually earn more time on the server by rating images. And so then at that point, what I'm saying about this is all purely probability is no longer true. It's also probability and a reward estimate. And then the question of like how much creativity is involved does start to get a little bit harder, because then at that point the model is kind of like placing its bets about what will a human like. So yeah, I'd say the conditional text generators trained with RL do get subjective enough that there's an interesting philosophical debate to be had there. That's not what we saw GANs doing a lot of the time. Yeah, I don't feel like I personally am the right person to have a strong opinion on it.
Well, no. Well, I think what's interesting is that often people who do make these claims about the technologies, they don't understand fundamentally how the technology works.
Yeah.
So they're not always fair or accurate in the way that they speak about them or criticize them. So I think, yeah, in this way, I think you're exactly the right person who knows.
Yeah, so I guess what I'm telling you is I understand the tech. There's a lot of stuff that's more about philosophy and art. And what I can tell you is, here's two pieces of tech. One I can say is definitely not creative. One where I'm like, oh, now I feel like let's call a philosopher. So the one that's definitely not creative is just, doesn't have to be, again, any generative model. You just say, here's a bunch of faces, train it with a purely probabilistic criterion to make more faces from the same distribution. I'd say that's imagination, but not creativity. Now, the next piece of tech is we say, let's have a person describe what kind of face they want it to make, and then have a person rate how artistically appealing they found the face that it made, and train it with reinforcement learning as well as the generative criterion. At that point, I'm now like, this is pretty similar to how a human artist learns from an art teacher. And it's actually hard for me to argue just on the basis of what the neural net is doing that it's not creative. I don't tend to anthropomorphize neural nets a whole lot, but I do like to try to say what are the actual processes that we do, and do machines do the same processes or not? If the neural net is able to generate something that is not the same as what it was in its training distribution, and there's something that people appreciate about it, that is starting to look to me a lot like it fits my conception of human creativity. And so this, at that point, I don't necessarily know that I'm like, okay, pin the blue ribbon on it, but I'm definitely at the point where I'm like, I want to at least talk to an artist about this before I conclude yes or no. So if that tells you, here's a technical person, we just found the boundary between where they're like, oh, definitely not creative, and like, oh, now it's hard to say. That's kind of where the wall is for me.
Yeah, that's really interesting. So a couple of artist takes that are pertinent here are Lawrence Leck and Mario Klingemann. I don't know if you're familiar with either of them.
I've heard of Mario Klingemann. It's not like I know him or anything.
Well, he created a autonomous or semi-autonomous artist called Botto. Do you know about Botto? It's kind of similar to what I think you were describing, where the machine creates images and then based on human reinforcement can change them. And yeah, you could sort of argue does have some kind of creativity, but I think where they get into some tricky territory is they kind of think of it as being fully autonomous, whereas I would probably think of that as being more partially autonomous. And then Lawrence Leck talks about fully autonomous, maybe AI artists, as something that would have the agency to choose to be an artist. So maybe if it was like a smart satellite that decided to stop surveilling on Earth and just decided to make art from its images or something like that. So there would need to be some kind of agentic choice from the machine. It couldn't be maybe programmed to do that like Botto is. But yeah, I wonder if you see fully autonomous and partially autonomous artists or things like that.
Yeah, I find like having some creativity in what you do as quite a lower bar than being a fully autonomous artist. Yeah, I see a pretty big gap between those two things.
Yeah, fair. Yeah, so you think what you described earlier was maybe the very beginnings of some kind of partial autonomy or creativity in an artist, but so you would think that that even is somewhat theoretical. So we're probably quite far away from full autonomy in an artist. Is that what you think?
Yeah, I think pretty far from full autonomy as an artist. To me, like that would kind of imply like an artist is expressing their own feelings, they have some kind of goals about what they want to communicate to other people about their own life, and like AI agents just don't have that kind of independent existence. I just don't feel like there's enough personhood for AI for them to even have the possibility of being an autonomous artist right now.
Whereas
creativity, I feel like there's some kind of a sliding scale. For purely generating more samples from the same distribution, I feel like that's 0. I feel like you can softly move beyond 0 with some of the image generation stuff that we're doing already.
I also want to maybe get your opinion on how impactful you think that these technologies will continue to be moving forward, because there is kind of still, there is a debate that is this all hype? In a few years, are we still going to be talking about these things? I mean, some people, I guess, do think that AI is still hype, or that deep learning is hype, or that there needs to be some kind of transition to neurosymbolic AI or something like that. So there's that kind of anti-hype, and then of course there's, on the other hand, there's the hype that generative AI is this new internet, or on scale or on par with the new internet or a new digital. And yeah, where do you stand maybe in between those poles in terms of hype and how relevant you think this technology will be literally, I mean, in something like 50 years, like, so on a time frame?
Well, no, I think it will keep going. There have been waves of more and more people paying attention to neural nets, right? Like neural nets were essentially dead from the most of the 90s. Andrew Ng is known as a big deep learning guy now. But when I first took his class as an undergrad, the Intro to AI class, I went up to him at the end of it and I said, well, wait a minute, why were there no neural nets in the class? And he said, oh, they don't work, don't bother learning about them. It was actually pretty much exactly that month that Jeff Hinton went and presented deep belief networks at NIPS 2006. They got a new state-of-the-art on MNIST beating support vector machines, which were the big academic thing at the time. So I think everybody has their moment where they feel like, oh, this is what put deep learning on the map. And for most of the world today, I think that's like ChatGPT. For me, it's deep belief networks beating support vector machines in 2006. So for everybody, it's like, oh, things are slowing down because ChatGPT 5 was a disappointment. I'm like, that's like such a small speed bump compared to where things have been going for, you know, like look at the time scale from the 90s. If you zoom out that far, that's like if you look at the stock market zoomed out since the 90s and you freak out about like a little oscillation from day to day. I don't really see this as any kind of significant slowdown right now. I think that these technologies are going to continue growing in capability and importance.
Yeah, and what's also so interesting about GANs is that they have this direct part in the story of what a lot of people think put deep generative models or generative AI on the map, which is text to image, because GANs were really a big part of the development of text to image. And when artists started combining GANs with other technologies like Clip, those are some of the very first widely available text to image models, and they were very artist driven. Yeah. How do you...
The generative model story and how it turned into media, I think that's a pretty useful one to tell. And I think one of the questions you had in the doc was about how did I first hear about generative models or something like that. So yeah, it's worth knowing. Generative models have been around for kind of a long time. Yoshua was training generative models of text, like neural language model type things. GPT, I guess it wasn't a transformer, so GP neural net. GP neural net 0 way back in the early 90s. I forget exactly when. So there were neural nets that generated text. Those were not particularly well known in academic circles worldwide. When I studied AI at Stanford as an undergrad in the 2000s, most of what I heard of for generative models were structured graphical models, where there's quite a lot of those in the deep learning book, and those have kind of died since I wrote the book. I think most people that study AI now don't learn about them at all. But quite a lot of my undergrad education was about structured graphical models. Like one of the main books that I read when I was learning was reading this like huge thick book called Structured Probabilistic Models by Daphne Koller and Nir Friedman. Daphne Koller was this genius that got her PhD at a super young age and then became faculty super young at Stanford, and she was still at Stanford teaching the course when I was there. And so at the time, people thought of generative models as these things where you would use them to represent like gene expression data, and they would be really, really bespoke for different kinds of data. So you might say, here's this gene that affects this enzyme and it interacts with this other gene that represents the thing the enzyme acts on. And you modeled directly how those two things interact with each other. And you draw a graph in terms of nodes and edges. So you'd have this thing that looks like it's really complicated spider web. Today, our generative models are these like really nice grids, like text is like one token influences the next token influences the next token. So it's just like a straight line in a grid. or like images, just two-dimensional grid. Back then, you would have these big spider webs of just like you've got thousands of genes, and then like each one is connected to like 5 random genes next to it. So these were things called like Bayesian networks or Markov random fields. And so they'd have these models, and then they would learn probability distributions over them, and then they could solve really small inference problems, like, you know, if we changed this one gene, what would happen to this other gene? They mostly avoided doing things like try to generate like the whole graph all at once. I took that class with my friend Ethan Dreyfus, who's actually the person that told me about deep learning originally. And so back then, generative models were like really this like hardcore science thing that you would use for like protein folding. I guess it still is now for AlphaFold. But so when we took the class, Ethan and I were talking, we're like, you know, someday people are going to use this to make video. You know, in 2008, we were talking about that. I wasn't thinking it would be me, you know? But yeah. I kind of took the class as like, someday this will be used to generate video. It's not going to stay used for genes forever. And then, you know, eventually Ethan told me about deep learning. I went off to study deep learning with Joshua. And then by 2014, you know, there was the idea of GANs. And at that point, that was kind of like, you know, I mentioned earlier, there were lots of pieces coming together at the party. Some of those pieces were, you know, since taking Daphne's class in 2008, I'd had this idea in my mind of, you know, someday people will use generative models to make video. We didn't do video in the first GAN paper, but yeah, we got there eventually. So I very much had been thinking there will be generative model for video eventually. If you look at my talk on GANs that I did at NIPS, we didn't get invited to talk at the NIPS main track where the talks are reviewed. We got invited to talk at a NIPS workshop, which is the like less prestigious unreviewed talk and reviewed track. I was saying basically we want to do video conditioned on actions, so you can make simulators and basically let agents think about their environment. So sort of imagine, what would my environment look like if I took specific actions? But a lot of what we were doing with the GAN was trying to steer things really strongly toward generating media and having imagination for agents. And kind of one thread was we were trying to lift the generative models world out of this like reason about how one gene affects one protein world, and lift it really strongly into the like GPU driven generate video world. And then the other thread was the deep learning community was already very much in the like, let's look at images world. They didn't need to be pulled that way. They were doing really small images.
Right.
And so, I mean, like part of what we did was we used convolution to like kind of try to push bigger images. We didn't get very far in the first paper because we only had 2 weeks, but a lot of what we did there was we pushed people more toward generation. The community had been really stuck on looking at samples and evaluating how likely they are. ICML 2013, that conference where I said I wrote the most cited paper, Max Out. There was actually a speaker there, Ruslan Salakutdinov, that came to the deep learning workshop. And during his talk at the deep learning workshop, he actually got up and said, you know, if somebody shows you samples in a paper, you should just regard it as quasi-fraudulent. What you really want to look at is the probability that a model assigns to samples in the test set. And that's the only way you can tell if a generative model is any good. He is right that there are a lot of problems with evaluating a model by looking at the samples that come out of it. For one thing, you could just memorize training set samples and then show samples from the training set, and it's actually pretty hard for a human observer to tell. You know, if you have a really big training set and then somebody shows you, hey, look, there's a really high quality photo of a face, like for all you know, it's just a training set sample. So you have to have evaluations that automate the inspection of samples to detect problems like that. And it's actually been pretty hard to develop metrics that look at samples. But the problem with what he's saying is that just looking at test likelihoods doesn't tell you anything about how good the samples look. There's a paper called A Note on the Evaluation of Generative Models that came out, I think, about a year after GANs. that actually demonstrates these two things are totally separate. You can have models with great test likelihood and terrible samples. You can have models with great samples and terrible test likelihood.
Right.
And for GANs, they don't even compute a test likelihood. So it's not that their test likelihood is terrible. They won't measure it for you. So you can't even run the metric. So for all kinds of things you might care about, like speech synthesis, chatbots, image generation, art, you can make things that do that task, but just aren't measurable in the way that the community was doubling down on in 2013. So in 2013, the community was saying, like, you really must measure the probability that your model assigns to test data. And in 2014, we kind of showed up with this shot across the bow saying, like, no, we're not even going to measure that. We're going to make this algorithm that doesn't even let you measure that if you want to come in as a third party and try to do it. We're going to double down the other direction on let's just generate really good images. And our images are so much better than anybody else's that we're going to get attention for doing it. It's pretty funny now. If you look back at the first GAN paper, like, you wouldn't think those images are good enough that they got attention, but they were. Somebody else's images were super blurry and things like that. And so a lot of what we did there was we really pushed things toward the samples were the product rather than the probabilities were the product.
Yeah, that's a really interesting way to think about that early impact and how GANs played this role in that time of proving that deep learning worked and that it could do something, and what it could do is it could now produce. You've now demonstrated like this compelling use case, and then yours was the first paper, but then this kicked off this really, really long line of future research. And yeah, I wonder if you can just talk about some of the subsequent research that carried GANs also from your invention to and continued sort of that trajectory that you set off. But yeah, like what were some of those the key drivers after you developed them?
Yeah, so I guess there's LapGAN was one of the first papers that showed that you could make much larger images than we did. And they did that by generating at multiple scales and sort of like generate an image, scale it up, and then add details to it. There was DCGAN in late 2015. And that was, in our first paper, we actually only had one convolutional layer. So DCGAN was able to be more serious about having multiple convolutional layers, like really taking a convolutional network and turning it upside down completely and having a fully convolutional generator. And they were able to get much better images. That's when GANs really started to take off. They were covered in Scientific American, and that's when there was a lot more attention coming into the field. After that, there was really steady growth in the quality of images and the size of images coming out of GANs. In terms of images, kind of the end point of where GANs ended up being really good was the different models of StyleGAN from NVIDIA, where they use kind of style transfer techniques at each stage of generation and kind of transfer styles onto the image to improve it at each step. And they can actually do things like render the same car from different viewpoints by kind of transferring a view style onto it. There's also been a lot of work on things like style transfer as an actual feature of the GAN rather than like an internal implementation component. So there's a model called CycleGAN that can learn to transfer styles across photos without ever needing to have supervised examples of the cycle transfer. So like, for example, if you want to turn horses into zebras, you can train on a bunch of horses and a bunch of zebras, and it will learn to turn a horse into a zebra. That's important because it can be really hard to get aligned supervised examples for supervised style transfer. Like imagine trying to go and get a zebra to stand in exactly the same position as a horse. Like you just can't do it. And so being able to learn the supervision learning to do the transfer in an unsupervised way is important for being able to do the task at all. And then there's been a lot of work on GANs for video as well. I guess there's also been stuff about like controllable representations for GANs, so that you can actually kind of change the hidden layer and get what you want in a predictable way.
Were you surprised at all that, so you were thinking about GANs in video in 2008 and still in 2014 is when you created them, but were you surprised at how quickly you were able to, or researchers were able to achieve video from this technique?
No, not really. I guess like we had been working on video in Joshua's lab as an input to classifiers since 2010 at least. I guess other labs had been doing video in other contexts too. I guess one thing to understand about GANs is they are really designed for speed and efficiency. A lot of how I got into deep learning originally is that I was a hobbyist video game programmer before I got into deep learning stuff specifically. A lot of I mentioned that my friend Ethan Dreyfus told me about deep learning. That was partly because he knew that I knew how to write code that runs on GPU. He had heard of Jeff Hinton's deep belief networks and was interested in whether it be feasible to implement them on GPU. So he heard of deep belief networks. Jeff was running them on MATLAB on CPU. Ethan realized that they were extremely parallelizable and that they would be more efficient to run them on GPU. He knew that I knew how to write GPU code for games and came and asked me, like, do you think we could run this on GPU? And this was like late 2007, early 2008. And we ended up building the first CUDA machine at Stanford in order to run them on GPU. I guess basically with GANs, I was trying really hard to make something that would be media generation friendly. They do everything in one pass. There aren't any funny like back and forth access patterns that would cause cache misses. There's not any kind of Markov chain iteration like you see with Boltzmann machines or diffusion algorithms. There's not any like one token at a time waiting for one token to generate before you generate the next token things like you see with GPT style models. So GANs are very much designed to do things like video really fast. That's one of their key advantages, and that's part of why they didn't get outdated for as long as they did.
Well, yeah, it's really interesting that you had that in mind for so long, and that's one thing that is related to culture and GANs is there's this idea that even artists have that I think it's a growing idea with artists that this idea between the distinction between artist and engineer is really not that important or is nothing, and that if you really take that to its logical conclusions, that you could argue that the greatest artists of this generation are engineers and are machine learning engineers. Some artists have made that argument, like Matt Dryhurst, and part of the reasoning for that is because they argue that the greatest creators make protocols, and then others can downstream kind of take advantage of that protocol creatively, and that machine learning engineers are some of the greatest protocol makers of this generation. So I just wonder what you think about that view that engineers and artists, the distinction is not really that different. And do you also see yourself as an artist?
So I do see myself as having artistic tendencies, but I actually see that as partially separate from the engineering work. I was actually interested in being a fiction writer. A lot of what I was interested in exploring in fiction was writing kind of psychologically realistic prose. There's a lot of modernist fiction that writes in a stream of consciousness style, where it's intended to be we see how a person's mind actually operates, and instead of kind of looking in from a third person perspective. I was also just really interested in figuring out more about like how do minds actually work. And somewhere along the way in my education, I kind of ended up going further on the figuring out how minds work thread than the writing fiction thread, and ended up putting most of my creative energy into machine learning research, and then found that I was actually feeling creatively fulfilled by doing the machine learning research, and didn't feel as much like writing fiction. Mostly is just it is a lot of emotional energy to do the research, but I don't personally see the engineering work as art. I think I think art it involves having some kind of a message, some kind of emotional expression, something that can actually be conveyed to other people. I feel like the protocol is more of a medium. I know like Andy Warhol said the medium is the message, but when he said that, I think he means more of like when the artist selects the medium for a particular piece of art, the artist is sending a message in the selection of the medium for that work, not that the person who invented a particular medium is sending a message. I don't think we really, we don't remember the person who invented Canvas as a great artist, even though they certainly have made a contribution to the art world. It's just a different kind of contribution. There's different degrees of artistic thought going into work in machine learning. Some algorithmic work requires more thought about like what does it mean to be intelligent and so on. Some is more just like, well, let's kind of analyze this and scale it up. Some of my work is a little bit more on the more artistic side, and quite a lot of my work is more on the like let's print out a big report and analyze it side. Certainly coming up with the idea for GANs had a bit more of an artistic feel to it than a lot of my days where I'm like, let's set a debug trace and print out what crashes.
Right. So it can kind of depend maybe based on what you're doing, but that you have felt creative fulfillment in your engineering work. And that's really interesting. And to the point where you didn't feel like another creative outlet was as necessary. And you understand the creativity involved with some machine learning engineering. Are you surprised at all by the amount of creativity that GANs have unleashed that have been beyond your control, but that you were directly maybe the first domino to fall, perhaps, or one of the early dominoes?
I think as AI has gotten more powerful, there is more thought about how much should we open source, because there is more of a risk of misuse in ways that could really harm people. But in like 2014, the kinds of things that we released seemed more likely to be used for artistic expression than for really harmful uses. And then so GANs have been used more or less as I hoped they would be. I think you can see from my first talk on GANs at NIPS, I did think that they would be used for simulation more than they have been, and that's not turned out to be a thing that was easy to do. So there's kind of been fewer engineering uses than I expected, but the artistic uses are more or less what I expected.
Did you have text to image in mind when you were thinking about GANs? Like, was that already something that you thought, oh, well, this will come, or oh, this will be useful, or oh, GANs will be able to help achieve this?
I don't remember how much I thought about text to image specifically. It's always hard to remember like what did I think when. I trying to get a handle on like what was I thinking at the time. I did look at my slides from NIPS 2014 recently, and I do talk about text to speech specifically. I think one thing to keep in mind is that back then there weren't good data sets for text to image. Today there's quite a lot of money in the field, both to train large models and to gather large data sets. In 2014, I was probably thinking more about like what's feasible for an academic to gather, and it would have been a lot harder to gather the kind of data set needed for text to image to work really well. In like 2015 or so, we did see a lot of the other direction of image to text for captioning. My guess is that it was probably a little bit hard to foresee getting the resources for text to image to work really, really smoothly for a long time.
Yeah, I mean, it happened pretty quickly after the paper. Like I know people like Sumith and Alec and Elman. Yeah, these are some of the early. Well, I guess what Elman was working on was not related to GANs, but yeah,
One
it was.
one thing that really has surprised me a lot is how much the industry is willing to pay for generative modeling. Like, you know, I mentioned how much effort I put into making sure that GANs are extremely sample efficient, and you know, for example, that's why they were able to make videos. Things like GPTs, you know, I just would not have expected that a company would be willing to spend what they spend for that. I would have thought that you would have to demonstrate more utility before spending that amount of money to train that kind of generative model. You know, a lot of how I personally got to GANs was assuming that it would just not be economically viable to train, you know, the kinds of models that we have today. It's not that the kinds of models we have today were impossible to think of. They're actually, you know, the transformer part is new, but that's like an architectural component. But the overall generative model algorithm we have of generating one token at a time, that's been around since the 90s. Joshua was already doing that, and we just kind of thought it was prohibitively expensive.
Yeah, it's interesting that one thing that was also mentioned in that NIPS 2024 talk was that GANs and the legacy of scale, and that they really demonstrated the power of scale. That's interesting now to think about how that got out of hand in a way, because of companies were willing to spend billions of dollars on this, on training the scale. So maybe that's what was surprising, especially at that time before there was really there was much commercial interest in AI at the time. These were still back in the university research lab days.
Yeah.
How do you feel about that legacy of scale today, when that's part of what a lot of the criticisms that AI and deep learning get, is that it requires all the scale and all these resources, and to get this data and the scale, that you often have to use unscrupulous means, and yeah, how do you think about the dangers and the flip side of some of this, with mostly the positives that we've talked about?
Yeah. I don't personally think that GANs are the cause of the current emphasis on scale. I actually feel a little bit like GANs are kind of a relic of the previous era of being careful about cost. But I mean, you are right that GANs were a place where we saw that there were big returns to scaling them up. But when we scaled them up, they were still relatively cheap. You know, we are talking like generally experiments run on a single machine, not run on a whole data center. I remember around like 2019, we started to see results with things like GPT type images beating GANs, and then GAN researchers messaging me saying like, look, this GPT beat our GAN results that we published, but like, look what they spent to do it. You know, they're running like a whole neural net per pixel. And in the GAN literature, we're running like a neural net per image. Like, what the hell? So it was surprising to me that people were willing to make that big of a leap in how much they would spend for relatively small improvements in the output of the image. I think where we really saw a change in spending habits is with the idea of scaling laws. People liked that there was this, I guess business type people liked that there was this function where you could predictably get more performance by putting in more resources. I'm a little bit surprised at how popular the scaling laws are, because what the scaling laws tell you, in my opinion, is actually not really what you would want. The scaling law is basically telling you at every point across the scaling curve, you get diminishing returns. And the diminishing is pretty strong. I feel like a lot of people saw it and said, like, oh, hey, at every point across the curve, you get returns to scale. And and I'm like, well, what did you expect? Yeah, of course there'd be returns to scale. What bothers me is that the returns diminish pretty fast. And people still kind of decided, like, yeah, let's just push to the right really hard across it, because we've now seen this curve that we think will go forever. I think that's where the increased spending came from. But yeah, I kind of feel like the GAN philosophy would be more of like, can we shift that curve down, or can we try to change the tilt of that curve somewhat, to not have to spend nearly as much? That GANs are more like, choose an amount that we're willing to spend, and then be clever to get really good results within that budget. The new approach is more like, well, let's not use artistic creativity about the algorithm. Let's just take a really dumb algorithm and pump money into it.
More brute force approach.
Yeah.
Yes.
Yeah.
Earlier, you demonstrated your skepticism about a fully autonomous artist, and is that related to also how you think about AGI? Because I guess that's one of the big things, and over the last few years in Silicon Valley, is to what extent people believe in AGI. That seems to.
I wasn't trying to imply anything about, like, is AI soon or far. I just mean, out of the systems we have now, are not AGI. Yeah, so like the systems we have now are not similar enough to AGI for them to be considered an autonomous agent. No, I think it's very hard to predict how long until AGI. I can talk a little bit about, like, how hard it is to predict how long until things. I've been really wrong in both directions. So in like 2007, I was working with Andrew Ng again, in his lab, which is also closely tied to a startup called Willow Garage. So I was working both places, Andrew's lab and Willow Garage, on household robots. And this was maybe before Uber existed, definitely before Uber was well known enough that I had heard of Uber. But the idea was basically Uber for, like, household robots. Our goal was, someday you'd have an app where, like, you summon a robot and it comes and, like, cleans your house and builds your IKEA furniture for you. And in 2007, we thought that was 10 years away. I'm the kind of person where, like, any large group I'm part of, I'm always questioning its beliefs and values and so on. And I was not questioning that one. I felt like we were on track. Like we had Larry Page came to Willow Garage to judge the intern contest, and we successfully had a robot waiter serve him. We didn't use a real drink because we didn't want the robot to accidentally, like, crush glass and spill it on him, but, like, it gave him a plastic drink bottle. And I was like, okay, yeah, not bad for 10 years off from target. And clearly we did not end up with Uber for robots within 10 years of them, even though I had felt like that was very easily on track. And then in, I guess I'd say, like, 2011, we were working on trying to use deep learning to solve supervised learning, where you look at images and you say what's in the image. And in Joshua's lab, we were working on really small images. We were trying to look at things that were like 32 pixels by 32 pixels and say, like, is this an airplane? Is this a car? And it wasn't going all that well. And I felt like it was, like, years and years until it was solved. And then in 2012, there was Ilya, Alex, and Jeff did ImageNet, and we just, like, really did not see that coming. We'd been focused on things like warming up with generative modeling before proceeding to supervised training. The generative modeling part was too expensive, so it was forcing us to use small models. we didn't realize that if you used big models and pure supervised training, you could get a lot further. And we were using other data sets instead of ImageNet. ImageNet just had a lot more examples, so you could get further with that. So, I mean, I feel like I've been very wrong in both directions. It's a lot easier to tell, like where are things eventually going? Like you can tell that capabilities will keep increasing, but it's hard to know like exactly when and in what leaps. And that's why you get people shocked by things like, oh, GPT-5 wasn't the leap we expected, and things like that. But you do tend to see like long-term things do keep getting more and more capable over time.
I guess it's one of the things that is the legacy of GANs too, and it's something that you've talked about before, and it was also mentioned in that 2024 the look back and at NeurIPS, and that's about the legacy of GANs and unsupervised learning. So you said in Wired in 2017, you said in the process, these two neural networks can push AI towards a day when computers declare independence from their human teachers. What was the role that GANs played ultimately in that progression to more unsupervised learning?
Well, I think we've ended up with unsupervised pre-training being a really big part of modern AI, and it just wasn't prior to GANs. I don't know how much you can say GANs are the reason that we have pre-trained transformers as a big part of modern chatbots, but I think GANs are a big part of why generative modeling was a big part of the conversation. I guess it's worth pointing out Alec Radford invented GPT, and he'd been working on GANs immediately prior to that. You could interview him about like what's the causality there.
Yeah, that link is really interesting because that I do think that the GAN story with Alec Radford is really interesting, and because he did go on to do GPT and Jukebox and these other multimodal realizations of deep generative models, but it's interesting that the very first thing that he gravitated towards was GANs.
Yeah. So I guess one thing that has shaken out a bit differently than I expected was, GANs are very sensory, right? I had been imagining that we would use unsupervised learning to discover the world in kind of the same sequence of steps that humans and animals do. Humans spend a significant amount of time being kind of pre-verbal, spending a lot of time seeing and hearing the world. You can actually hear in the womb before you're even born. And then after you're born, you can see. You spend a lot of time moving around, sticking things in your mouth, but not really talking very much. And then eventually you start talking, and you don't really start learning a whole lot from like massive amounts of text and things like that until you're quite a bit older, right? The way the AI industry has gone is like we bypass all of that, and we just go like straight to tokens now, and just kind of like from the moment of creation, the GPT is just getting like high level cognitive tokens and is bypassing forming these visual representations of the world. So I would have thought that you needed to spend the time on the sensory motor stuff to form concepts of objecthood and so on, or that you wouldn't be able to like have enough of a concept of things that you're referring to understand the tokens very well. But it seems like you're able to get pretty far in a world of pure tokens. So that's one thing that really surprised me about the pre-training world that I expected versus the pre-training world that we got. I thought we would need something kind of not necessarily the GAN algorithm, but kind of like pre-train on images, videos, audio, and then move on to learning a lot about knowledge from texts. And it's been surprising to me that you can just go straight to pre-train on text and actually seem to derive meaning from it without knowing what it refers to, without having like an external referent.
That does seem to be so interesting about how deep generative models have developed, that text and language seems to be the kind, in some ways, the winner, and that it can now be used in this multimodal way to create all these different things. And maybe this is the last thing we can talk about, but I'm interested in that Platonic. Are you familiar with the Philip Isola's Platonic representation hypothesis? Do you know? Have you heard of it before?
I've met Philip Isola before, but like several years ago when we were both working on GAN stuff more. I'm not familiar with that particular term. So I'm reading quickly. Neural networks trained with different objectives on different data and modalities are converging to a shared statistical model of reality in their representation spaces. Oh, that's pretty interesting, actually. So just so he's saying like lots of neural nets trained on different things all come up with similar internal representations, basically.
Right, and that so that might in some ways explain why like these vision models are learning the same representation as text models, and or that Isola seems to be saying. And yeah, I just wonder what you think about that, and then also just you said something before about how AI can imagine worlds, and or eventually we'll be able to imagine kind of the world in more realistic detail and realistic images and sounds. And it seemed like you were thinking about a multimodal future. And you said that this will encourage AI to learn about the structure of the world that actually exists. Yeah. Do you see any relationship there between that idea with Philip's or Isola's Platonic representation hypothesis, that these models are learning some kind of structure, underlying structure of reality? Or yeah, how do you think about that?
Yeah, I think they're related. He seems to be, I'm only briefly seeing what he's arguing here, but he seems to be going a step further and saying that, that it's okay if you don't have overlapping experiences, that, maybe if one model has only vision and text and another has only vision and audio, that they can still learn the same representation of the same thing. Yeah. That's pretty interesting. One other thought I have about this that strikes me as kind of interesting about his hypothesis is, I worked in machine learning security for several years. And neural nets don't learn just the same good representation. They also learn the same mistakes. So when you attack a neural net and try to intentionally fool it, and you find inputs that they misclassify, different neural nets will misclassify those adversarial examples in the same way. So even though those input points are just kind of like random garbage, it may look like random garbage to you or me, but like the same neural net, like imagine I'm trying to fool a face recognition system to get access to a secure facility, and I want it to think that I'm, the director of the facility or something. I might be able to train my own neural net to recognize faces, and then make like weird glasses I can wear that make my neural net think I'm the director of the facility. If I then wear those same glasses and go to the facility, their neural net has a pretty high probability of being fooled in exactly the same way as my neural net, because of this convergent representation property. So it's kind of interesting. What he's describing is a known property that's considered a security risk in the machine learning security literature. Except there we're looking at two different neural nets trained on different examples from the same domain. So like two different neural nets trained on vision. But I hadn't heard of there being convergence across, like vision and text. So that's pretty interesting to me.
Yeah, it reminded me of some of your ideas. And then, well, yeah, I mean, this was a real treat. I mean, you're somebody who will be part of the story of AI art history. I mean, the GANs will be in AI art, or just art history textbooks moving forward, and it's going to be part of art, whether people maybe realize it quite yet, but it will be. And yeah, so it was really really meaningful to be able to talk to someone who's had such an impact on art, and ask them about some of these questions, and ask them firsthand about that impact. So yeah, really, thank you so much. It means a lot.
Thank you. Yeah, I really liked your timeline, and yeah, I'm looking forward to seeing your other work. Yeah.
yeah, I hope we can be in touch and maybe talk again someday, maybe hopefully meet in person sometime. But yeah, I really appreciate at least today and the time.
Oh yeah, very welcome. All right, thank you.
All right, thanks, Ian. Bye. Take care.